Welcome to qnawire.
So all the objects start at the same height and they all have the same mass. And one more thing is they roll without slipping. So they have their mechanical energy conserved. So we know that by conservation of mechanical energy, we mean that the total energy at initial position must be equal to the total energy at the final position. And if we call this as our initial position, let's call it number one. So subscript one relates to all the energies corresponding to this place. And when the object moves to the base, we call it point two, which is the total energy corresponding to this point. Now we can see here that all the objects start from rest. So that means at this point, they will have the potential energy, but there's no kinetic energy. So we can get rid of this part. And this point, if we set y equal to 0 here, so y2 becomes 0 and y1 over here becomes h. So we can get rid of um, the potential energy at this point. So we have potential energy is equal to kinetic energy. And also we see that the object rolls as well as it moves through the slope. So it will have the rotational kinetic part and the translational kinetic part. So we'll be using F equals ma for the translational part, and for the rotational part we'll be using tau equals I times alpha. So that's when we do the force calculation. And as we mentioned, for kinetic energy calculation, we'll have total kinetic energy, which is a combination of translational kinetic energy plus rotational kinetic energy. So this translational part is easy. It's just half of mv squared, where v is the velocity at this point. So let's call it vcm. And rotational part is just half of I cm omega squared, where omega is the angular velocity at this point. So we can combine all those together and see what we get. So first of all, before doing that, we see that this moment of inertia is different for different objects. And let's call this ICM, which is equal to CMR squared, where C is a number and that will vary depending on what object we're choosing. For example, if we're choosing solid cylinder, then C is 2 over 5, and so on and so forth. So, yeah. So if we actually use this equation now, as we mentioned that I will be chosen as CMR squared. So we start with the energy conservation, and as we mentioned that we got rid of the kinetic part. So this is 0, and at this point this one is 0. So at the top we have the potential energy, so mgh is the potential energy, and the kinetic part is half mv squared plus I omega squared, half I omega squared, where I is cmr squared. So that's what we wrote, and if we combine everything together, we see that it's half v times 1 plus c. From there, if we write v squared in terms of the other parameters, we see it's 2gh divided by 1 plus c. So there will be m here. So let me write it here. And we got rid of m's on both sides. Right. So yeah, we know v now, and we can figure out which has the highest velocity from there. And if an object has the highest translational velocity, that will take the minimum amount of time to reach at the bottom, because they will have the highest average velocity as well. So highest v means minimum time. And if we look at this equation carefully, we see that 2gh, this part is constant. The only thing that's changing here is c. So that means the velocity is inversely proportional to c. So if c increases, velocity decreases. Now, we know that for solid sphere it's 2 over 5, for solid cylinder it's half, hollow sphere it's 2 over 3, and hollow cylinder it's 1. So whichever has the highest c will have the lowest velocity and hence the maximum time, and whichever has the lowest c will have the highest velocity and hence the minimum time. So we see that from this chart, the solid sphere has the lowest amount of c, which means it will have the highest velocity, so it will take the minimum time to reach the bottom. So that's why from our diagram in the question, a will be the solid sphere, then following that will be b, and then it will be c, and then it will be d. So that's the in increasing order of time. So in this way the time is increasing. That's increasing time. So this way it's decreasing time. So for part B, we need to figure out which has the greatest kinetic energy. Now part B is easy because it will have the same kinetic energy, and the reason we say that is hidden in this equation, because we see that the kinetic energy at the bottom is equal to the potential energy, and since all the objects have the same mass, so the potential energy is conserved, or the potential energy is constant for all of the objects. So if the potential energy is constant, then kinetic energy must be constant, because we have an equality sign in between them. So for all the objects, we'll have the same amount of kinetic energy. So that's why we have same kinetic energy. In part C, we have to figure out which has the greatest rotational kinetic energy at the bottom of the ramp. So for rotational part, it's just half of I omega squared, and that'll change because we have a C factor here, which depends on different objects. So if we write that in terms of v squared, then we can substitute this v squared value from this expression, and if we do so, we end up having this expression over here. Now I want you to look at this equation carefully, and it might be confusing to see how to get the rotational kinetic energy, but stay with me. I'll walk you through it. So first, what does that equation tell you? We have mgh, which is constant, so the rotational part entirely depends on this c, right? And we see that to get the highest rotational kinetic energy, this must be lowest, right? So 1 plus 1 by c must be minimum, and if that's minimum, then overall this term becomes the maximum, and that's hence we have the maximum rotational kinetic energy. And how do we make this minimum? So again, we have a c factor here. So if c is very large, then this term is very small. On the other hand, if c is very small, then this term is very large. So to make this minimum, we need to make this entire thing minimum, and since 1 is constant, let's get rid of this part as well. So all we have is 1 over c, and we have to make 1 over c as a minimum quantity. So how do we make that? So we need to take c greatest among so we need to take the greatest c value among the 4, and that will give us the minimum. And if we look at this chart one more time, we see that the hollow cylinder has the maximum c value. So in our case, the hollow cylinder the hollow cylinder will have the highest c, and hence the maximum rotational kinetic energy. Now in part D, we need to find out the coefficient of static friction, and to do so, we have to make a free body diagram of the object. So as you can see, I've already drawn that. So we have the object over here, and the weight of the object is vertically downwards, and that's why we have two components that's acting on the object. One is mg cosine theta, which is just opposite to the normal direction of the force. And then we have mg sine theta, which is along the ramp, and since the frictional force is acting in the other direction, so they will try to compensate for each other, and we have a resultant acceleration in the downward direction. So if the resultant direction is downward, that means we can say that this quantity of force is greater than the frictional force, and that's why we subtract this force from the frictional force, which gives us m times a, or the resultant force. And we need that equation for mu s. So one thing we should remember here is Fs, where Fs is the coefficient of static friction times n, where n is the normal force. And since there's no movement in this direction, so n should be equal to mg cosine theta. So this quantity can be written as mu s mg cosine theta. So as we can see here that mu s is hidden in this quantity, so we need this equation to find out mu s. Now for the torque portion, we'll have Fs times r, because we don't need mg because mg is acting through the center. So if the force is acting through the center, there's no torque involved there. So we'll just take the frictional force part. So we multiply that with the radial vector to get the torque, and that should be equal to the center of mass moment of inertia times alpha. And for the rolling without slipping condition, alpha should be a over r, where a is the linear acceleration. And from the previous parts, we have already seen that I should be equal to mc r squared, where c is again it will depend on different objects. From here, we see that if we solve for it, we have Fs equals m times c times r, because we can get rid of the r's on both sides. So we have this quantity left. And from here, we can write ma equals Fs over c. And this ma can be substituted back to here. And that'll give us an expression in terms of Fs. So we did that, and we got this expression. So from here, if we take Fs on the right side and take that common, because it's same on both of the terms, so we take that outside the parenthesis. So we have this expression, and then we replaced Fs, and let me write that down one more time. Fs is mu s times mg cosine theta, and we replace that number over here. From there, if we write this expression in terms of mu s, we get this following expression, where mu s is tan theta over 1 plus 1 over c. Now this term right here is constant because we have a constant angle in the slope. So again, this part is changing. And for the rolling without slipping condition, we need the maximum mu s, because if we take the maximum mu s, then other objects will obviously roll without slipping. So to take the maximum, this term must be minimum, or in other words, if this is minimum, 1 is constant, so 1 over c must be minimum. In other words, c must be maximum. And we know that for hollow sphere, or sorry, for hollow cylinder, c is 1, which is maximum. So we can take that value. So we can take the maximum value, which is c equals 1, and using that we can figure out the coefficient of friction. So we take c equals 1, and if we do so, we see that mu s is equal to tan theta over 1 plus 1, which is 2, and that gives us tan theta is 35 degrees. Divide that by 2, and that gives us 0.35. So that's the maximum coefficient of static friction. Thank you.